Hello, my name is Ryan Markowitz, and this is my wrap-up reflection for the real-time systems class I just took. I actually leaned on this class quite a bit for my senior design project, which is a solar tracking robot called Solaris. So most of what I'm going to be talking about comes straight from actually building that firmware. So, in terms of like the technical insight of this class, I would say the biggest shift for me was actually learning to think in terms of concurrency instead of just straight line execution. Because before this class, I mostly wrote code that ran from top to bottom. I guess the exception of that would be also this semester I took enterprise computing, where I also did multi-threading programming in Java. But besides that, these are the only two classes where I've done any type of concurrency. So RTOS forced me to think about a bunch of tasks all running at once and fighting for same hardware and same memory space as well. So what actually changed my system of thinking was the timing side. So doing response time analysis, I would say was a really big thing that I learned in this class. Because instead of just running the code and just hoping that everything keeps up, you can actually mathematically prove if everything will meet its deadlines in like the worst case scenario, right? Also, learning about how locks and resources like counting semaphores, for getting a pool of resources and mutex, which mutex inherently get priority inheritance. So you're not getting priority inversion as opposed to like a binary semaphore. So once I started designing, for the worst case timing instead of average, you kind of look at systems differently. So a challenge that I actually faced didn't come directly from this class, but from my senior design project where I used a lot of the concepts from this class to write the firmware in RTOS for Solaris. So I actually encountered many concurrency bugs, but I'm just going to talk about one specifically. So in the automatic move portion of my code, the robot is supposed to check the energy, gains over time, and if there's a significant power drop, it should, make a move decision essentially, and then move the robot out of shade if there's shade. And what I had found was when I moved it into automatic mode, that decision was never getting fired. And what ended up happening, and I figured it out, the code for reorienting the solar panel on the top of my robot was taking a mutex. It was giving it back, but the period at which it was running was going so fast that it was essentially starving that mutex. So the energy monitor task could never even see it. So I had to change the code up a little bit to make it not run as fast, to just find the sun, like completely settle, and then I run that every 30 seconds as opposed to like every 150 milliseconds. And that helped that mutex be freed up for the energy monitor. And the reason I was trying to grab that mutex is because I didn't want it to read the energy and store it into the buffer to make that move decision while the robot was moving, because obviously there's a huge power drop when motors are moving. So that was just like a really interesting concurrency bug that I actually ran into in real practice. And as far as real world application and what is kind of coming for me next, I already used it in the real world, as I mentioned, like on my Solaris project. But also I'm lining up and heading into a firmware QA role. So I won't be designing time systems from scratch, but I'll likely to run into firmware that uses it, and I have to validate and make sure that all of that is running properly. That's probably going to be part of what I'm doing and part of my job. So overall, I would say that this class has helped me immensely understanding real-time systems and what to look out for, especially as I go on into my career. So yeah, that is the conclusion of my wrap-up for real-time systems. I really enjoyed this class, and I look forward to interacting with more real-time systems in the real world.